guys, so this is a paired sample t-test, and guys, the only difference between the previous concept and this one is that here you would identify questions where the data should be existing in pairs. So of course, for data to be existing in pairs, the number of data values for one variable should be equal to the number of data values for the other variable. So that could be a case in most of the situations, but sometimes examiner might trick you with data that's not paired, but he may keep equal number of data. So the criteria is not equal number of data. But the data exists in pairs when they have a correlation between them. So that means X1 is pairing with Y1, X2 is pairing with Y2, X3 is pairing with Y3. So I mean, you can't shuffle them. You can't write X1 with Y2. You can't write X3 with Y1. So you would see a certain correlation between every pair of data, and that would be the reason for you to say that's a paired data. I've given you a couple of examples here, and you will see more examples as well as you'll practice questions. But if you have a set of data of husband and wives, not men and women can shuffle around, right? If I take a particular data from 6 men and random 6 women, then obviously they are not existing in pairs and they can shuffle around. But if it's like husbands and wives, of course, it exists in pairs. So there's a correlation between them. So if it's that way, then you would obviously keep them in pairs. Instead of 6 boys and 6 girls, if you have a pair of 6 siblings, so boys and girls, that means sibling boy and sibling girl, then it would be a paired data. So anything of that kind, or maybe a test on the same person before and after. Maybe you test the heartbeats or measure the heartbeats of a person before the exercise and after the exercise, or you probably give him a medicine and you are judging his pulse rates before and after the medicines. So if you would see that kind of a situation, you'd identify that the data is in the form of pairs, and you have to perform a paired sample t-test. So the steps are, I mean, if you're performing a paired sample t-test, or even if you're finding out the confidence interval for paired sample data, you will first find out the difference of the set of data. So you subtract them and you'll calculate the differences. So, and then you'll perform the test on those differences. So just like you calculate the mean, you will calculate the mean of differences, you will calculate the variance of differences, but that would be the difference of sample, the variance of sample, and then you will apply the formula n upon n minus 1 to get the unbiased estimate of the variance of population of the difference of mean. And then you will write down the distribution of the test statistic. It will always be t-distribution. It will always be a smaller set of data, something lesser than 30 for x1 and x2. It will be a t-distribution. And then you can write down the t-distribution for the data, and then find out, perform a hypothesis test in case if it's a hypothesis testing, or you can also find the confidence interval. So it says carpal tunnel syndrome is a condition which affects a person's ability to grip. So researchers tested a certain treatment for the syndrome, which was applied to 8 randomly chosen persons, pre-treatment and a post-treatment. So it's the same person, patient 1, pre-treatment, post-treatment. So of course, the data is existing in pairs. You can't reshuffle the data. It's for the same person, pre-treatment and post-treatment. So it's a paired sample t-test. The test is very similar to what you did earlier on. I mean, the only thing is that you will do it on the difference of the data. So you find out the differences. I could have done 24.3 minus 28.3, and I would have gotten negative answers. In that case, my alternate hypothesis would be less than 0, because I'm testing if the post grip has increased. So if the mass of the post grip has increased, so of course this must be bigger than this. So that's why I subtracted this, and my alternate hypothesis is that it's greater than 0. But the thing is that, I mean, it really doesn't matter much if I do x1 minus x2 or x2 minus x1, but I have to write my alternate hypothesis accordingly. If I'm looking for it to increase, so that's why I did this minus this, and I took alternate hypothesis as greater than 0. I'll come later on, but I took out the differences, and then I calculated the mean, and then I calculated the variances of the differences, and then I calculated the unbiased estimate of the population variances. And my required assumption would be that both the distributions are following normal, both are following normal distribution. And after doing that, I can find out the variance of some variance, estimate of population variance of difference. My null hypothesis is that there's no change. Alternate is that post-treatment grip is more. So I write down the distribution with n minus 1. So guys, this is like 8 and 8. So your number of data is not 16 because you're performing the test on the differences. Your number of data is not 16, it's actually 8. So degree of freedom would be 7. You will find the critical region. You had to perform the 1% significance level. So you took a 99% probability with 7 degree of freedom. Your test critical value is coming out to be 2.998. So after getting the critical value, you had a test value of d bar over here, which is 2.2125. You can put that value over here. Mu comes from the null hypothesis, and your test value is lying in the critical region. And hence H0 would be rejected in favor of H1, and hence the mean grip has improved.